Okay, so today we are going to be factoring polynomials. Today we're going to cover the difference of squares and the sum and difference of cubes. Now, we've already seen factoring out a GCF and factor by grouping. So now two more different factoring techniques. And again, remember your quiz is going to say factor completely. It's not going to tell you which factoring technique to use. Now, I highly recommend that you memorize the perfect squares. Okay, I'd say up to 20. You should already know the perfect squares from 3rd grade because you learned your times tables. And what I mean by perfect squares is when you take a number and you square it, like for example, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. And I would say up to 20 would be a good starting point because really 1 through 12 you should know. So that way when you see a problem that has a 4 and a 9 in it, you're going to know that potentially it's the difference of two perfect squares. Now, notice the name of this, the word difference. In math, difference means subtraction. So when we have two perfect squares, they're always going to have a subtraction sign in between it if we're hoping to factor it. If it's got an addition sign, chances are the only thing we might be able to do to it is factor out a GCF. Now, as far as the cubes go, I'm not going to expect you to memorize, a lot. I'd say up to 5 to the 3rd power. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. You might get something larger, but for the most part, they're going to stay within reason up to 5 cubed. Now, little fun factor trick if you need help memorizing beyond 12 times 12, 13 squared or 13 times 13 is 169, and 14 squared, if you flip the 6 and the 9, it's 196. Another fun fact that I found, just a side note, 12 times 12, everybody knows is 144. If you flip the 12 and make it 21 times 21, it's the answer of 144 backwards. So little, things that come up with numbers that have little patterns, but you don't need to know that, just a fun fact. Okay, so let's go on. So when we're factoring polynomial or binomials, and again, binomials are going to have two terms, just like a bicycle has two wheels. You need to first always check to see if there's a GCF or a greatest common factor. And then from there, we'll see if we can do anything else with it. And we'll see if it's going to be the pattern of difference of squares or sum and difference of cubes. So the patterns, and we talked about this a little bit when we foiled, the pattern when I have two perfect squares is going to end up being you're going to square root the two terms, and then you'll put it into the binomials, one with a plus sign and one with a minus sign. So for example, if I have 4x squared minus 9, if you can realize that 4 and 9, or 4x squared and 9 are perfect squares, in order to factor this, all you do is find the square root of each term. So the square root of 4x squared is 2x. The square root of 9 is 3. We'll write it, each of the answers of the square root, and then one will have a plus sign, one gets a minus sign. Now it doesn't matter if you write 2x minus 3 or 2x plus 3 first. Yes?
Can you do that if it's a plus sign in the middle and then just make it double plus?
Nope.
Okay.
Okay, because if you FOIL that or multiply it back, you're going to get a middle term.
Okay.
So down here at the bottom, notice my big caution. There is no such thing as the sum of two squares. So if there's a plus sign in between them, you're not going to be able to factor it. Okay, so this does not work. Okay, now, however, if I gave you something like this, and I know I'm jumping ahead here, but let's say it's 4x squared minus 100. No, plus 100. Okay, if I gave you something like that, at first glance you're saying, oh, those are perfect squares, but it's a plus sign. I can't do anything, but we can do something. What did we learn yesterday? Everybody heard what she said? We look for a GCF. You should always look for a GCF first. So in this particular problem, the only thing I would do is divide by the GCF, and then I would stop here. I would not be able to factor that, the plus sign. Good? All right. Now, this is the pattern for the sum and difference of cubes. When we get to that, this is going to be at the end of the slides. We're going to talk about it. You're going to memorize these patterns for the sum and difference of cubes. And I have a little acronym, and I call it SOAP, and that'll help you remember the signs. So my SOAP acronym, this first parentheses has the same sign as the original problem. This one is opposite of the original problem, and this last sign is always positive. So same sign, opposite, always positive. But when we get to the cubes, we'll talk about this a little bit more. Let's try some practice of factoring the difference of two squares first. Now, as far as the cubes go, generally a lot of Algebra 1 courses don't teach you to factor cubes. That's really more in Algebra 2. But the difference of squares, you should have seen this in your Algebra 1 course. This shouldn't be new to you. Okay? So again, the easiest way is you're going to look to see, are both numbers in your problem perfect squares, and is there a subtraction sign in between them? But again, before you begin, look for a GCF first. Can I divide 16 and 25 by anything? No. No, right? Is 16x squared a perfect square? Yes. Is 25 a perfect square? Yes. Perfect. I can do my pattern here. So I'm going to square root the 16x squared, square root the 25. The square root of 16 is 4. The square root of x squared is x. Square root of 25 is 5. 1 gets a plus sign. 1 gets a minus sign. Now, I highly recommend when you're first practicing with your homework to check your answer. And the way that you check is you would FOIL this. If it doesn't go back to your original problem, you've got something wrong somewhere. It might be a sign, it might be a number. So this was the R3 homework where they gave you this and they told you to multiply. So if it just says factor, we're done right here. But if you have time, FOIL it or distribute it. See if it goes back. 4x times 4x is 16x squared. 4x times negative 5 is negative 20x. 5 times 4x is positive 20x. And then 5 times negative 5 is negative 25. Notice when I distribute or FOIL, the middle term is gone. And it did go back to my original problem, so it does check out. So again, FOILing is going to save a lot of yours, especially when we get to the trinomials on Monday. Let's try the next one. Again, remember, first step, look for a GCF. Okay, so first glance, 36, 81, they look like perfect squares to me, right? But can we simplify that first? Okay, good. We're going to divide them both by 9 first. So 9 and 9. So I write the GCF on the outside. Remember, in the parentheses is going to go what I get when I divide. So 4z squared minus 9y to the 4th. Now, if what remains in that parentheses can be factored further, I need to keep going. Are 4 and 9 perfect squares? Yes. Yes. Now, when your exponents are even numbers, notice how it's a 2 and a 4? The variable exponent, when it's even, is a perfect square. Okay, so now I need to break this down. I need to break the 4z squared 9y to the 4th down. So again, in my answer, I still write the 9 GCF I pulled out. I'm going to square root this, square root this. Square root of 4z squared is 2z. The square root of 9y to the fourth, remember you divide the exponent by 2 when you square root it. So this becomes 3y squared. And again, 1 gets a plus sign, 1 gets a minus sign. I can't factor any further, so I'm done. Yes?
Can you show us what would be like if you didn't take out the greatest common factor?
If I didn't on this one, then your answer would have been this. If you didn't pull the GCF out, if you just square rooted 36 and 81, you would have gotten 6z minus 9y squared and 6z plus 9y squared. Soon as you see that, hey, wait a minute, I can still divide 6 and 9 by something, then that should have been a clue. You should have gone back and pulled a GCF out. Okay? Everybody see that? So that would be a clue that, oh wait, I can make this smaller still. Let me go back to the beginning and pull the GCF out originally. All right, next one. Is x squared and 25 both perfect squares? Yes, they are. So I square root of x squared is x, square root of 25 is 5, and then 1 gets a plus sign, 1 gets a minus sign. I can't factor any further, so I'm finished. Again, if you have time, FOIL it. Make sure it goes back. Pretty good? Let's try the next one. This one's backwards now. It's the same thing. Again, 25 and 1 are perfect squares. So again, square root of 25x squared is 5x. Square root of 1 is 1, because 1 times 1 is 1. And then again, put 1 with a plus sign, 1 with a minus sign. Next one, I'll first glance, see if there's a GCF. I can't divide 49 and 64 by anything, so I'm gonna, and they're both perfect squares. So square root of 49 is 7a. Square root of 64b squared is 8b. 1 with a plus, 1 with a minus. And you're done. Pretty good? Anybody still need it? Let's try another one. All right. This next one, I know I only told you to memorize up to 20, but 625 is actually 25. So if I square root it, again, remember for the variable, you're going to divide that x to the fourth by 2. So this will become 25x squared plus 1 and 25x squared minus 1. Now again, your instructions are going to say factor completely. So notice the first one, I can't do anything because it's a plus sign and it is the sum of two perfect squares. But this guy over here, they're still perfect squares. I can keep going. So the first one I'm just going to rewrite. And then the second one, I have to factor again. I square root the 25x squared and I square root the 1. So this becomes 5x plus 1 and 5x minus 1. Yes?
Oh, wait, everybody.
Okay, so you may have to keep going. Again, the instructions on the quiz will say factor completely. So it's not going to say, hey, this one, you're going to probably have to factor it more than once. So just be aware to double check that you have factored it completely. The next one, can I factor that? Are they perfect squares? Yes, question?
Why would you only factor one side instead of both?
Okay, so if you remember from the beginning slide, the name of the lesson is the difference of two squares. So I can only factor when it's a subtraction sign. So there's no such thing as the sum of two squares, which leads me to the next question. Notice it's x squared plus 100. Because this is a plus sign and not a subtraction sign, I cannot factor that. So you would either tell me it can't be factored, you could just rewrite the problem. You could also write that it's prime. So can't factor, just rewrite it, or write that it's prime. Okay, so there is no such thing as the sum of two perfect squares. Now, what if I gave you, and I know I did this at the beginning, what if I said it was 98x squared plus 50? What could I do with this one? Divide by 2. I could pull a GCF out. Everybody see that? Now, once I do that, look what remains. Can I keep going? No, because it's a plus sign. Okay, at first glance, you're going to think, oh, 49 is a perfect square, 25 is a perfect square, but I cannot go on because this is a plus sign. So I would stop right here. Yes?
How would you know, when you can and when you can?
Okay, so you should always look for a GCF first in any type of factoring problem. Then from there, if after you divide it out, if you have two terms, if it's a binomial, and if this is a plus sign, you can't do anything else. It has to be subtraction to keep going. All right, next one, we're going to factor it a whole bunch of times. Are we ready? All right, x to the 16th minus 1. Perfect squares? Yes, it's an even exponent. Remember, when we square root a variable with an exponent, we're dividing that exponent by 2. So this will become x to the 8th when I square root it. So x to the 8th plus 1, x to the 8th minus 1. Can I still keep going? Yes. This one's going to stay the same because it's a plus sign, and there's no such thing as the sum of two squares. But this one I'm going to break down into, again, I'm going to divide it by 2, and it becomes x to the 4th. Plus 1, minus 1. Still got a big exponent there. I can keep going. X, exactly. So x squared plus 1, x squared minus 1. Now these guys, the 8 and the 4, these guys still keep coming down. Can't forget about them. Am I done?
No.
One more time. All right, so the x to the 8th plus 1 comes straight down. Same thing with the x to the 4th, this one, and now this one more time. X plus 1, x minus 1. Now I'm finally finished. Yes?
Wouldn't you go straight to the x4 since you're doing the perfect square on each of them?
Okay, so when I square root a variable exponent, I don't do the square root of 16, I divide the exponent by 2. Does that make sense? So the only time you actually square root a number is when it's a coefficient. Does that make sense? So the difference is if you square root 16, yes, that's 4, but when I square root a variable that has an exponent of 16, when you square root a variable exponent, you divide it by 2. Okay, so here, I'm sorry? Good, beautiful. All right, can I factor out more than just a 5?
X2.
Good. I'm going to do both the 5 and the x because x is in common to both. So now when I pull it out, I get x squared minus 4. Am I finished?
No.
Keep on going. So 5x, write that down, and then factor this into x plus 2, x minus 2. Now I'm finished. And again, remember, you can always multiply it back to see if it goes back to the beginning. It's your check. Next one. What should I do first? Divide by 4. Beautiful. 4 and 100 are GCF, are perfect squares, but I always need to look for the GCF first. And now, again, I still have the difference of two squares, so I factor this one more time. And we have one more for the difference of two squares. Now we'll move on to the cubes. Okay, again, look for a GCF first. Notice they both have the letter U and they both have the letter V. So my GCF here is going to be UV. I'm going to divide it and I get V squared minus U squared. Difference of two squares. So write the GCF and then V plus U, V minus U. And oops, and you're done. Now the perfect cubes. And again, you may not have seen this next part. This is really probably more Algebra 2 concept. So again, memorize the patterns. And again, remember that SOAP acronym will help you. So here's how the SOAP works again. So if your original problem has a subtraction sign, the way that we're going to do this is we, instead of square rooting the numbers, we are going to be cube rooting the numbers. So when I cube root, I would divide the exponent by 3 now. So this will give me my A, and this gives me my B. And then from there, we plug it into the pattern. So A minus B, same sign as the original problem. Then the next parentheses, we square the A. Opposite sign, that's the O in SOAP. And we multiply A and B. And then the last term, AP, always positive. And you square the B. And then the same thing if it were the sum. Same sign, opposite, always positive. Let's try these with some numbers. It'll be a little bit easier. Okay, so the first example. Again, you're going to look at the problem, see if there's a GCF. If there's not, then the next thing we're going to look to see are our numbers perfect squares or perfect cubes. If your exponent on your variable is a multiple of 3, that should be a clue that it's going to be a cube. If it's an even number, that should be a clue that it's a perfect square. So again, the process is to cube root both of the numbers. So again, what I have right now is A cubed minus B cubed. So once I cube root it, my A value for my pattern is going to be the cubed root of x cubed, which is x. My B is the second number, and the cubed root of 1 is 1. Now I'm going to put it into the pattern. Remember, the pattern is A minus B, same sign as the original problem, and then A squared, opposite sign, A times B, plus B squared. So, same sign, opposite sign, always positive. So, let's fill it in. So, my A is x minus 1. I square the A, so it becomes x squared. I multiply A and B for the middle term, and then I square the B for the last term. Whenever you factor these cubes, this thing won't be able to be factored anymore. So once you apply it to the pattern, you're done. Let's try another one. Can I divide 8 and 27 by anything?
Yeah.
No, right? So are they perfect cubes? Yes, they are. So again, this is really supposed to represent A cubed, and this is my B cubed. So remember, to get A, I cubed root this one, and I cube root this one. So my a value, the cube root of 8 is 2, and the cube root of x to the third is x. The cube root of 27 is 3. And now I put it into the pattern. Again, if it helps you to write out the pattern each time, you can do that. So again, remember SOAP, same sign, opposite, always positive. So let's put it in. So a minus b, 2x minus 3. Square the a. Now let me write it this way just so you can see. So a squared is 2x squared. Then the middle term is the a times b, which is 2x times 3. You don't have to show this, but I just want to show you how it's coming about. So this 2x, when I square it, is going to become 4x squared. The a times b is 6x, and then the 3 squared is 9. So that would be your final answer. So remember, for this first term, this a squared here, you square not only the x, but also square the 2. So just be careful on that. Good? Yes?
For difference for the difference of cubes or the sum of cubes, x can also be to the power of any multiple of 3, right?
Correct.
So it could also be like 6 or 18 or 12?
Yes. Perfect. Everybody good? All right, let's try another one. Again, here we go. This is what she just asked. This little exponent doesn't have to be a 3. It can be a multiple of 3. Okay? So again, when I cube root this, I'm going to divide that exponent by 3. So my a value here is going to become 3x squared, because 6 divided by 3 is 2. Okay? And then the cube root of 1 is 1. And now I'll put it into the pattern. Now this is the sum. So again, remember the pattern here. Same sign, opposite sign, still a times b, and then the last one is always positive. So 3x squared, same sign as the original problem. Square this thing. So this becomes 9x to the fourth. A times b with opposite sign is 3x squared, and then square the b. And you're done. Again, this trinomial will never be able to be factored any further. So you're just cube rooting it and putting it into the pattern.
For the one above, what did you do for 8 that you got to?
The cube root of 8. So I have to figure out what number times itself 3 times gives me 8. So if I do 2 times 2 is 4, times 2 again is 8. All right, 2 more and we're done. Again, sum of 2 cubes. Again, cube root the 64x to the third, cube root the 1. So this one gives me my a value. Cube root of 64 is 4. Cube root of x to the third is just x. Cube root of 1 is 1. And now I put it into the pattern. Same sign. Square the a. So 4 times 4 is 16. X squared. Opposite sign. Multiply a and b, and then square the b. Now, the next one was actually a mistake on my part, but it's a good learning experience. Remember, what did I tell you those exponents needed to be when it was a perfect cube?
Multiple of 3?
Can I divide 8 by 3? No. So in this case, I can't factor this. So you would have said can't factor, or you would have said it's prime. But now I'm going to change this problem, and I'm going to make this, let's make it a 9. Let's make it a multiple of 3. Okay? So if the exponent can't be divided by 3, it's not a perfect cube. So now it's a perfect cube because I can divide that exponent by 3. So again, my cube root of 8m to the third is going to be 2m. My cube root of this 27n to the ninth is going to be 3n to the third. Remember, you divide it by 3. And then now I'll put it into the pattern. So again, same sign. Square this one. Opposite sign. Multiply these two. And then square the last one. And you're done. All right, so the next slide is your homework. This is due on Monday. It's not very much. It's only 7 problems, okay? So again, if you find you need more practice, let me know. I can give you some. Try to do the evens. Then you can check them with my book. Again, the difference of 2 squares should have been a review of Algebra 1. The cubes, probably not so much. But some Algebra 1 courses might have taught it to you. So again, work on memorizing those perfect squares and the perfect cubes. Again, this weekend, look for a study guide for the quiz. I'll probably post it sometime this weekend.